now we are going to see the properties of carboxylic acid. Our first property is physical property. Physical property, that is whether it is a colorless, whether it has any smell, boiling point, melting point, solubility. So these are the physical properties. So first, aliphatic carboxylic acid. What is aliphatic? Aliphatic means that is compound without a benzene ring. Compound without a benzene ring. That is without a benzene ring. Is called aliphatic carboxylic acids. That means lower aliphatic acids. That is up to 9 carbons. C1 to C9. C1 to C9. Or colorless liquid. Colorless and it is liquid in state. Unpleasant odor. Unpleasant odor. Higher acids. That means more than C9 or waxy solids. Odorless. Odor means no smell. Due to their low volatility. That means volatile. That means easily vaporized. Easily vaporized. Easily vaporized. Now next property is boiling point. Boiling point. So carboxylic acids. Normally carboxylic acids have higher boiling point. Then aldehyde. Aldehyde means compound containing CHO group. Ketone, CO and even alcohol, bond OH. So normally carboxylic acids, among all these functional group, acid, bond COOH, acid have a higher boiling point of comparable masses. That means similar masses, more or less. Why? So this is one of the reasoning question. The carboxylic acids have higher boiling point than aldehyde, ketone and even alcohol of comparable masses. Why? Due to the extensive association, the carboxylic acids are associated with each other. So, association of carboxylic acid molecules. Why this association takes place? They are associated due to intermolecular hydrogen bonding. Inter means between two molecules. Intermolecular hydrogen bonding. Intermolecular hydrogen bonding. Intermolecular hydrogen bonding. Now, the hydrogen bonds are not broken even in vapor phase. Even it is in the vapor phase, the hydrogen bonds are not easily broken. Therefore, carboxylic acids exist as a dimer. What is dimer? See this. That is two carboxylic acids attached with each other. So, carboxylic acids exist as a dimer in the vapor phase or in aprotic solvent. In the vapor phase or in aprotic solvent. Aprotic, that means it does not containing H+. Aprotic means solvent which does not containing the H+. Is called aprotic solvent. So, this is one of the carboxylic acid. That is acetic acid, CH3COOH. This is another acetic acid. This oxygen carries partially negative charge. This hydrogen carries partially positive charge. And this negative. Here, this is partially negative. This is partially positive. So, there occurs an attraction between the positive and minus. So, there occurs a hydrogen bonding. This is minus. There occurs a hydrogen bonding. This type of force of attraction between positive and negative. This is one of the weak force of attraction which is called as a hydrogen bonding. Hydrogen bonding. So this shows the carboxylic acids exist as a dimer. Carboxylic acids exist as a dimer even in the vapor phase or in the aprotic solvent. Now we are going to see the solubility. Solubility. Solubility means whether it is soluble in water or not. Solubility completely miscible. Simple aliphatic carboxylic acids. That means carbon up to C1 to C4 are miscible. Miscible means soluble with water due to intermolecular hydrogen bonding. Yes, this solubility means the intermolecular hydrogen bonding is between acid and water. Boiling point means between the acids. Here between acid and water. Intermolecular hydrogen bonding between acid and water. Now, let's see the hydrogen bonding between acid and water. RCOOH, acid. This is another acid, C double bond O, OH. This is a water molecule. So, 3 acid molecules, partially positive, partially negative. Partially negative, partially positive. Positive, negative. So, the force of attraction between the positive and negative charges attract each other. That attraction is weak. That force of attraction is called as a hydrogen bonding. That weak force is called as a hydrogen bonding. But here, in solubility, the intermolecular hydrogen bonding is between acid and water. Is between acid and water. So, this is a hydrogen bonding of acid with water. Solubility. Next reasoning question is, the solubility decreases with increase of carbon atoms. Why? We know the alkyl group increases means solubility decreases. Yes, due to the increased hydrophobic. Hydrophobic means water repelling interaction of hydrocarbon part. What is that hydrocarbon? Alkyl or aryl. So, why the solubility decreases with increasing number of carbon atom? Due to the hydrophobic nature of alkyl group. Aromatic carboxylic acids nearly insoluble in cold water. Even in cold water, it is insoluble. It is insoluble in cold water. Benzoic acid, we know the formula, C6H5COOH. Now, the carboxylic acids also insoluble in cold water, but soluble in less polar organic solvent like benzene, ether, alcohol, chloroform. So, it is insoluble in water, that is cold water, aromatic. Cold water, but it is readily soluble in benzene, that is organic solvent. It is readily soluble in organic solvent. Soluble in organic solvent. Now we are going to see the chemical properties. Chemical property, reaction involving cleavage of OH bond, that is C double bond O, OH no. So here cleavage of OH bond. Acidity, first property, reaction with metals and alkalis. Normally the carboxylic acids like alcohol, we already studied, alcohol liberate hydrogen with electropositive metals like sodium and NaOH. Yes, similar to alcohol, carboxylic acids also evolve hydrogen with electropositive metals. What is electropositive metals? Which have a tendency to give H plus readily. That means readily donate electron, that is electropositive metals, and if it loses the electron means it forms a salt. With the alkali similar to phenol. Unlike phenols, means not like phenols, acid react with weaker bases also, with the sodium carbonate and sodium bicarbonate. Sodium carbonate and sodium bicarbonate. Alkalis, this is strong acid like NaOH. This is a strong base, yes. It is a weaker base, sodium carbonate and sodium bicarbonate. Even with weak bases also, the acid has a tendency to react and evolve the carbon dioxide. That is, now the reactions. These reactions used to detect the presence of carboxylic acid in an organic compound. Yes, that is with sodium metals, electropositive metals and alkalis. How this example, acetic acid. Carboxylic acid react with metal. We know it is a electropositive metals. Electropositive metals in the periodic table is in the first group. Yes, that has a tendency to donate the electrons easily. Tendency to donate the electron easily. So, acetic acid react with sodium. That similar to alcohol, it also has a tendency to liberate hydrogen. It also has a tendency to liberate hydrogen. Yes, acetic acid, we take 2 molecules of acetic acid, 2 moles of sodium. Hydrogen, OH bond is breaks, no? H2 goes out, Na added here. This is sodium acetate. We already know CH3COOH is acetic acid. CH3COO minus is acetate. CH3CO is acetyl. We discussed, no? It is acetic acid. Now, H is removed. So, 8. Instead hydrogen we have Na. So, sodium acetate. Sodium acetate. Not only with the electropositive metals, but also with the sodium hydroxide, it has a tendency to form a salt. How it forms salt? H2O goes out. Base means H2O goes out. Metal means it liberates hydrogen. And now it has a tendency to react with the weak bases like sodium carbonate and sodium bicarbonate, no? Yes. This is sodium bicarbonate or sodium hydrogen carbonate. Sodium bicarbonate, or it can also be written as sodium hydrogen carbonate. Acetic acid. How this carbonate is there in the reactant means it has a tendency to liberate carbon dioxide. One oxygen is there. This hydrogen with one oxygen and this hydrogen goes out as water. So one carbon dioxide goes out leaving one oxygen. Here H2 and O goes out as water. Now we get CH3COO Na, sodium acetate, common salt. In this reaction, the carbon dioxide removed is from sodium bicarbonate. Important one mark. We know acid has a tendency to liberate carbon dioxide with the sodium bicarbonate. Whether the carbon dioxide comes from carboxylic acid carbon dioxide or with sodium bicarbonate. It is liberated from sodium bicarbonate, not from carboxylic acid. So it is important one mark. Now the carboxylic acid dissociates in water to give resonance stabilization. So that only it does not undergo even though it has a carbonyl group, it does not react with many addition reactions like aldehyde and ketones due to the resonance stabilization of carboxylate ion. Yes, carboxylic acid or COOH with water. What happens? H3O plus. H plus goes out, leaving this minus. So this becomes O minus. So resonance, it involved in resonance. How this happens? This bond comes here. This is already satisfied with 4 valency. If it wants to form a new bond, means it has to lose one bond, no? So it becomes O minus. This arrow mark represents the resonance structure. This resonance gives a stability to this carboxylate ion. Stability to the carboxylate ion. This is equivalent to, that means the minus for both oxygen, no? So it is present in the middle. The above reaction is in equilibrium. That means acid converted to carboxylate ion. Again it has a tendency to form a acid. So there exists an equilibrium. We can write the equilibrium constant. If any equilibrium reaction is exist means we can able to write the equilibrium constant, no? So the equilibrium constant is K equilibrium equal to product concentration by reactant concentration. That is, this water comes this side. Since it is a constant, water is in excess, no? So the change is negligible. So it remains as a, consider as a constant. So constant into constant, that is Ka. Ka is nothing but the equilibrium constant of acid. Acid dissociation constant. K equilibrium, we know equilibrium constant. Ka is a acid dissociation constant. Dissociation constant of acid. A represents acid. So Ka equal to H3O plus or COO minus by or COOH. This Ka indicates the strength of the acid. Ka indicates the strength of the acid. So it indicates the strength of the acid by pKa. Strength of the acid by pKa rather than Ka. Even though the Ka or pKa, both of them explains the strength of the carboxylic acid, we know pKa equal to minus log to the base 10 Ka. Log to the base 10 Ka. For HCl, pKa value is minus 7.0. For what is this? Trifluoroacetic acid. If hydrogen is there means it is acetic acid, no? Halogenation takes place in alpha carbon. So it is trifluoroacetic acid. Trifluoroacetic acid. pKa. The pKa for this is 0.23. 0.23. And the strongest, this is the strongest carboxylic acid. Since the fluorine is highly electronegative, no? It has a tendency to attract the electron from hydrogen and H plus easily removed. So it is the strongest carboxylic acid. If any electronegative atom is substituted means it is a strong carboxylic acid. Next is aromatic carboxylic acid, that is benzoic acid. Its pKa value is 4.19. Similar acetic acid, pKa is 4.76. From this we can understand Smaller the pKa value, stronger the acid. That means pKa value decreases means the acidity increases. pKa decreases means the acidity increases. So, smaller the pKa, stronger the acid. That means acid means which has a tendency to donate proton. Which has a tendency to donate proton. So, pKa less than 1 is called strong acids. pKa less than 1 is called strong acids. And pKa 1 to 5 is called moderately strong acids. Moderately strong acids. If 5 to 15 means weak, that means the pKa increases means the acid strength decreases, no? So, less than 1 strong acid. Then up to 5 it is moderately strong acid. Then 5 to above 15 it is a weak acid. And greater than 15 means extremely weak acid. So, this for the 1 mark. The common concept is pKa increases means acidity decreases, or pKa decreases means acidity increases. The carboxylic acids are weaker than mineral acid. Even though it is a strong acid, but it is weaker than mineral acids, that is inorganic acids like HCl, H2SO4, hydrochloric acid and sulfuric acid. But it is a strong acid than alcohol and phenols. 1 mark. Weaker than mineral acid, but stronger than alcohols and phenols. Now, why carboxylic acids are more acidic than phenols? Another important reasoning question. That is, why carboxylic acids are more acidic than phenols? Why? Since the conjugate base of carboxylic acid is stabilized. We already discussed, no? Carboxylate ion is stabilized by resonance. So, the stabilized by 2 equivalent resonance structure, in which the negative charge is at the more electronegative atom. That means it is between more electronegative oxygen atom. Yes. What is that explanation told? The conjugate base. What is that conjugate base? That is carboxylate ion. What is conjugate base? That means a species left after the removal of hydrogen. Left after the removal of hydrogen. That is conjugate base. After the removal of H plus, carboxylic acid is changed to carboxylate ion. It is stabilized by resonance. And the negative charge is between the oxygen atom. Let's see the reaction, how it is placed. That is organic acid or COOH, general acid. With water, we know H3O plus goes out. This plus and this minus comes here, and this COO minus. This is a conjugate base, that is carboxylate ion. Carboxylate ion. This carboxylate ion involved in resonance. This minus comes here, and this shows the resonance structure. Resonance structure. So, this is the resonance structure of carboxylate ion. Here the negative sign placed in the highly electronegative oxygen atom. Highly electronegative oxygen atom. Now, the conjugate base of phenol. This is about a carboxylic acid. Now, about phenol. In phenol, the phenoxide ion is the conjugate base. Non-equivalent resonance structure. The resonance structure is not in equivalent, in which the negative charge is at the less electronegative carbon. Here it is negative charges at the carbon. There it is in oxygen. In this, the oxygen, it is in oxygen. But here it is in carbon, in phenols. Let's see this. C6H5OH is phenol. C6H5OH is phenol. And react with water. We already know H plus and this minus goes out. This goes as a H plus, H3O plus. And now C6H5O minus. This is called as a phenoxide ion. This is called as a phenoxide ion. Let's see the resonance structure. Let's see the resonance structure. Yes, this is a phenoxide ion. This minus comes here and this bond shift here. This carries the minus sign. This carbon carries the minus sign. So, minus. This minus, whether it has it in, whether we need to put the plus here? No. If the lone pair is shared means, This oxygen carries the plus sign. But here minus. Involved in the reaction. No need to put minus means extra electron. Minus means extra electron. So this minus comes here means double bond. This carbon is already satisfied with 4 valency. So one bond comes here. It becomes minus. We already studied in the phenol alcohol lesson. No? So this minus comes here and this bond comes here. Minus. This minus involved in the resonance. So this is already satisfied with 4 valency. One bond shift to here. See all these. The minus is present in the carbon. So in acids it is present in oxygen. In phenols it is present in carbon. Further, the negative charges delocalized. Delocalized means it is for all the carbon atom, no? Delocalized. And 2 electronegative oxygen atom in carboxylate ion. 2 electronegative oxygen atom in carboxylate ion. Whereas it is less effectively delocalized over 1 oxygen atom. What is that? In carboxylate ion, 2 electronegative oxygen. But in phenol, 1 oxygen atom and carbon. What is that? In carboxylate ion, that is CH3, C double bond O minus, it is involved in resonance. What is that? CH3, C, O minus, double bond O. So here it is between 2 oxygen. But here in phenol, oxygen and carbon. So this is less effectively delocalized than the carboxylate ion. Therefore, the carboxylate ion is more stabilized than phenoxide ion. So, carboxylic acids are more acidic than phenol. What is the concept? In carboxylate ion, the resonance is between 2 oxygen. In phenoxide ion, the resonance is between oxygen and carbon. Therefore, the carboxylate ion is more acidic than phenols. Now, what about the effect of substituents on the acidity of carboxylic acid? Whether any substituent is there means whether it has a tendency to affect the acidity or not. Let's see this. Effect of substituents on the acidity of carboxylic acid. The substituents, that means methyl, ethyl or chloro, bromo, like that, affect the stability of conjugate base and also affect the acidity of carboxylic acid. Yes, the substituents affect the carboxylic acid. How? We are going to see how it affects the substituent of carboxylic acid. Now, whether the electron withdrawing group is there means, if the electron withdrawing group is there, withdrawing, that means which has a tendency to attract the electron towards itself. It has a tendency to attract the electrons towards itself. Electron withdrawing group. If electron withdrawing, that type of electron withdrawing group, EWG, that type of electron withdrawing group is there means it increases the acidity by stabilization of conjugate base. By the stabilization of conjugate base. How? It gives us stability through delocalization of negative charge. Electron withdrawing means plus effect. If alkyl group is there, it has a tendency to donate. No. So, or by the resonance effect. Yes, it is minus. Now, electron withdrawing group. Attract the electron towards itself. So, this carbon donates its electron. Electron withdrawing group attract. So, if attract means, let's see that. CH2 Cl. C double bond O, OH. This is O bond H. This is electron withdrawing group. That means it has a tendency to attract the electron from this carbon. So, it attracts from this carbon. This becomes electron deficient, no? So, this attract from this carbon. This becomes electron deficient. This attract from this oxygen. Now this subtract from this hydrogen. So now hydrogen has only one electron. No? That is accepted by this oxygen. So the H plus is easily goes out. So electron withdrawing group increases means acidity increases. Acidity increases. What about the electron donating group? If electron donating group is there means the acidity decreases due to the destabilization. Let's see this. Electron donating group. Donating group means CH2, CH3, C double bond O, OH. This is electron donating group. This has a tendency to donate to this carbon. This becomes electron rich, no? So this donates to this carbon. This becomes electron rich. This donates to oxygen. Now it becomes electron rich and donates to oxygen. Whether the H plus goes out, we are donating the hydrogen and place it there. So H plus does not goes out. That means automatically the acidity decreases. Acidity decreases. Therefore, electron withdrawing group increases means acidity decreases. Now, the increasing acidity order of some groups. Increasing acidity order of some groups we are going to see. That is, increasing order of some groups first. That is, phenyl, iodide, bromine, chlorine, fluorine, cyanide, NO2. These are highly electronegative. So, attract electrons. Attract means more acidic. Then electron deficient. Cyanide is also electron deficient. Fluorine is electronegativity. Now chlorine, bromine, iodine and phenyl. This is also highly electron donating. So, this is highly electron attracting. This is donating. So, it becomes weak acid. Phenyl group means it is weak acid. If fluorine is highly electronegative, no, so it is more acidic. Now, acid, increasing acidity order of acids. Increasing acidity order of acids. Trifluoro, CF3 is more acidic, no? Then 3Cl, less flow. Among the periodic table which is highly electronegative, fluorine is more electronegative. So, it has a tendency to accept the electrons more readily than others. So, this is more acidic. Chlorine is less electronegative than next chlorine. Here 3 chlorine is there, here 2 chlorine. So, this is more acidic than 2 chlorine. NO2 is electron deficient than Cn. So, NO2 and then Cn. Now, one alkyl group increases. Fluorine, that is more electronegative. Then chlorine, then bromine. Here, there is no alkyl group, no? So, this is more Here, the Cl is in the third carbon. So, the electronegativity decreases. When it is closer means it is more electronegative and acid strength increases. It is far, so it is less acidic. Now, phenyl. Phenyl means it is electron rich. Now, another one ethyl. Here, 2 alkyl group is there. So, less acidic. Carbon, that means the carbon atom increases means acid strength decreases. Carbon atom increases means acid strength decreases. Now, the direct attachment of some groups increases the acidity. What are the groups which increases the acidity? Phenyl and vinyl. What is phenyl? C6H5. Vinyl, CH2 double bond, CH. If these two groups directly attach to the benzene ring, it has a tendency to increases. But we studied it decreases, no? In contrary to our expectation, it increases the acidity. Why it increases the acidity? By resonance effect. By this arrow mark shows the resonance, no? CH2 double bond, CH is a vinyl group. Here we have a double bond. So one bond shift here. This bond is for both the carbon atom. So if we shift one bond here means this become deficient and this become rich. So this plus comes here. So plus here. This bond comes here, so double bond. So this carbon is already satisfied with 4 valency. If it forms a new bond means it has to shift one bond to oxygen. So it becomes O minus. So this resonance structure leads to the increase in acidity. This resonance stabilization increases the acid strength. Because of the greater electronegativity of sp2 carbon. In that vinyl, we have a carbon-carbon double bond, no? So, the sp2 carbon to which the carboxyl group is attached. So, the electronegativity arises since the double bond is attached to carboxyl group. Now let's the electron. So from this we studied electron withdrawing group increases means it increases the acidity. Electron withdrawing group increases the acidity. Electron donating group decreases the DD. Remind that. Donating decreases the acidity. Donating decreases the acidity. Let's see some compounds with example. That is, see this compound. What is the name of this one? 1, 2, 3, 4. Fourth carbon we have a methoxy group. Methoxy, methyl oxy, methoxy. So 4-methoxy. Without this compound group means it is called as a benzoic acid. So 4-methoxy benzoic acid. 4-methoxy benzoic acid. Let's see. The oxygen carries 2 lone pair electrons. So whether it is electron withdrawing group or electron donating group. This is electron rich, no? So it is a electron donating group. Electron donating group increases means acid strength decreases. We studied electron donating group increases means acidity. Acidity decreases. So let's see this. The electron donating group donates the electron to this carbon. This becomes electron rich. So donates to next carbon. This becomes electron rich. Donates to next. In this manner, the electrons are donated to hydrogen. Whether the hydrogen goes out? No, it does not go out. It stays here itself. So the acid strength decreases. This is a normally standard compound, that is benzoic acid. Here what is the name of this compound? First 1, 2, 3, 4. Fourth position we have a nitro group. So 4-nitro benzoic acid. Now tell me whether this nitro group is electron withdrawing or electron donating group. Electron withdrawing group. So what is the concept we studied? Electron withdrawing group increases means acidity. Electron withdrawing group increases means acidity increases. Acidity increases. Acidity increases. So this NO2 group increases the acid strength. That means it has a tendency to accept the electron. So accept the electron means in this arrow. Donated means this arrow. This goes in this manner. Here it accepts. So it becomes deficient. This accept from next carbon, next carbon, next carbon. This accept from this carbon. This accept the electron from hydrogen and the H plus goes out. And the H plus goes out. So it is its acid strength increases. Its acid strength increases. So the pKa, from the pKa value we can explain whether it is a strong acid or weak acid. No. The pKa for electron withdrawing group is 4.46. Without any group it is 4.19. With electron withdrawing group it is 3.41. What is the concept we studied? pKa value increases means acid strength decreases. Comparing these three, this is more value. So it is less acidic. This is more acidic. This is medium. So normally acidic. So normally the pKa value increases means acid strength decreases.